In this demo, we show how to synthesize a Grassmannian matrix of minimal coherence following Trop's algorithm. We aim to create a matrix of size 50 rows by 100 columns with the lowest possible coherence. We start by synthesizing random such matrix and normalizing its columns. This is our initial matrix A. As can be seen in the code, the entire process operates on the Gram matrix G, so we start by computing it as A transpose A. We apply 10,000 iterations in which we update G with 3 different steps in each iteration. First, we identify the entries in G that are the top 5% in their absolute values and shrink them by multiplying them by 0.95. Secondly, we take the resulting Gram matrix and force it to have a rank n using SVD. Lastly, we multiply G from the left and the right by a diagonal matrix that causes the main diagonal of the result to be 1s. This parallels a normalization of the columns of A. The iteration ends by a printout of the temporary results. We show the iteration number and the ideal mu we aim to get. We also show the average absolute value of the off-diagonal elements in G. We shall call this the average coherence. Finally, we show the current mutual coherence, the most extreme value in the off-diagonal elements in G. Once we conclude the iterations, we use the SVD in order to extract the resulting A from its Gram. This parallels a square root computation. Let's run this algorithm and see how the results evolve. One can clearly see a consistent descent in the 2 coherence values. Jumping to the end of this run, we see that we came quite close to the ideal Welch bound value. Let's present the results visually in order to understand them better. In figure 1, we show the mutual coherence, the mean coherence, and the ideal value, all as functions of the iterations. This graph clearly shows the tendency to get closer and closer to the Welch bound. In figure 2, we plot the entries of the absolute value of the Gram matrices after omitting their main diagonal. The initial Gram has a wide spread of values from 0 all the way to 0.5 and beyond. The final Gram is getting very close to the ideal form of having all of its entries equal and the lowest possible.